All right. So, number 11. How much force is required to stretch a spring? 19.5 centimeters. The spring constant is 51 newtons per meter. Ah. So, I would start off my Y for this one probably with something like the further you stretch a spring, the more force is needed. And maybe the spring constant is different, I'm going to put it, for every spring. Yeah, that's about it. That's all I would need for my Y. Basically, I'm showing that I understand Hooke's law without saying Hooke's law. Although I could say, the further you stretch the string, more force is needed. It's shown through Hooke's law or something like that, if I wanted to. Well, how would you define it? Okay. Yeah, as long as your definition wasn't the equation. Yeah. But if it was, hey, Hooke's law, this is the definition of Hooke's law. Yeah. Was it in this class yesterday that we determined that one of the things copied was from England? Or was that in my other class yesterday? One of my other classes, how we were working on the Y's, checking the Y's. We found one of them that had been copied because of the spelling in it was English. And no one in there knew how it was. They were like, why is that spelled wrong? So, yeah. Alright, so let's see, we need to start with the valid physics equation. I can go up to my handy dandy equation sheet, right? And get Hooke's law, which is right there in the middle. So, it says the force on a spring is negative K delta L. Now remember that negative is just there because the spring always wants to go back to its original state. So if I stretch it, and I move it to the right by stretching it by moving it to the right, the force is going to go to the left. That's that negative, right? That's why there's a negative in front of the K. So in this one, though, they just asked me, what do they ask me? What is the force needed in newtons? Okay, so quite frankly, let's see. I want the force. They give me K. I can drop the negative because I'm only interested in the magnitude of the force, right? They don't. They say how much force is required to stretch a string, not in what direction is the force. So let's just. My spring constant is 51 newtons per meter. So 51 newtons per meter. I stretch it a distance of 19.5 centimeters, so 0.195 meters. And I'm done. Yay. Oh, this is good. I haven't done this one yet. So number 7. chemistry question. Maybe. Well, they want to know the number of electrons and the number of protons in the system. And the system is entirely of protons and electrons. And they tell us the net charge and the total mass of the system. And I like that they use the proper terms, net charge and total mass. So, I would probably start off with something like the net charge is due to any unmatched charges. Right? Because they're saying net implies that you combined all of them and you're only looking at the ones that don't cancel out in one way. Yeah. So when you're talking about net force, you could have 20 net forces, 20 forces, they're all combined, some cancel, some don't. You end up with a single outcome. So that's the idea of net. The total with the mass is just, let's sum up all the masses. None of them can mass cancel out? No. So, unless you have antimatter, we're not up to that yet. Yeah, we'll get there. So, the net charge is due to any unmatched charges. You could go as basic as electrons have one quanta of negative charge, and protons have one quanta of positive charge. I really wish they named them Fred and Ethel or something like that rather than positive and negative. Make a lot less screw up.
Isn't it in like circuits, like electrons flow negative and positive?
Yeah, remember we talked about how Franklin screwed us up? Yeah, he thought positive charges moved. Wrong. So, I think that's about it. So, this is one of those, what physics equation? Let's see. Well, we could use that the total charge is n times the number of quanta. Oh. Oh, okay.
That's like, no one else can pick for it.
Okay. So the total charge is, this is total charge, is due to the number of quanta and times one quanta. So let's see what the problem tells us about. It says we have, this is a net charge. So my net charge is positive. Is your net charge is positive? Jackie, is yours? You looked bored, so I called on you. Okay. Never mind then. Anybody's negative. All right, we'll go with everyone's positive. So, what does that mean? Do we have more electrons or protons if our net charge is positive? More protons. No, remember that's how big it is. It'd be negative, like mine. If mine said negative 1.89, so we have more protons than we have electrons, and we know the total mass. Okay. So here we go. So the let's figure out how many extra protons we have. So our Q for me is 1.89 times 10 to the minus 15th coulombs. So 1.89 times 10 to the minus 15th coulombs equals number of protons. Now this is just the extra protons times the charge on each proton, which is 1.602 times 10 to the minus 19th coulombs. And I get the number of protons from that. Right? I mean, think about it in other ways. You have 30 things, and if you have 30 things, each one is a pack of 2. How many packs do you have? It is. That's in coulombs, the fundamental charge. Remember, they made coulombs huge. I use 1.602. If you look, your book uses 1.6. I don't know. I like the O2.
It's personal.
It is. I got myself 11,798. Let's see. What do they want to know? Let's see what they're going to. I'm going to keep all my digits because I would keep them in my calculator. No units there. That's the number of extra protons. That's the number of protons that don't have a partner. Let me give you a simplified form of this without all the fancy numbers and see if you can figure it out. 30 equals n times 5. How would you solve for n? So how do you solve for n?
Divide by 1.602
Yeah.
What
I mean, sometimes when the numbers just get in the way, right? So throw in easy numbers and see the math, and then go from there. So now remember, this isn't the total number of protons. This is the number of protons that don't have a partner. All right? So if we wanted to know the total number of protons, let's call this, we want to know the total number of protons. We're going to call that, let's call that big N. The number of protons is going to equal the number of electrons plus small np, the number of protons we just figured out don't have partners. So, we're going to need to use the total mass to figure this out. So, moving on to this part, the total mass is going to equal the mass of the protons and plus the mass of the electrons. I don't love that notation, but which is the number of protons times the mass of a single proton plus the number of electrons times the mass of a single electron. Right? If you wanted to know the total mass of something, total mass of grapes, and you had yellow, you had green, and you had red grapes, and you knew the mass of each individual red grape, and you knew the mass of each individual green grape, and how many you had of each, you could find the total mass. That's the same idea. Gabe, did you have a question? So, we know lots of this stuff, right? We know the total mass. Total mass for me is 4.56 times 10 to the negative 23rd kilograms. I'm going to move that over now, because that equals the number of protons, which I don't know, times the mass of a single proton, which they tell me is 1.673 times 10 to the negative 27. Kilograms, plus the number of electrons times the mass of electron, which is 9.11 times 10 to the minus 31st kilograms. Let me make sure of that one. Yep. I read it off my problem. Mass of a single proton. Yeah, that's right. I didn't love my notation, but now, do I know any relationship between the number of protons and the number of electrons? Sam, what do I know? Ah, cool. Wait, two unknowns, I can just solve it now. I can just use algebra, right? You can solve both simultaneously, or you could substitute in for the number of protons. Remember this, we're really saying is Ne plus 1197.75281. So I could take that, and I could substitute that whole thing in here, right? Or I could put both equations into Wolfram, with separated by a comma, and have it solved. Give it a try. See what you come up with. We'll pause for a minute while you try it, and I'll try mine. What I did is, rather than put the two equations in, I put in my summary. I put in this and solved it. I did my substitution. So back here, see, I substituted in here for the number of protons. So my number of electrons is 15,450. Let's see if that works. That's my number of electrons. Yep.
You go back
to Wolfram? Yeah. So I took that expression I had for x, and I put it in there in place of x.
Yeah, so you got rid of number of protons, made it number of protons, got rid of it, which number of protons equals Ne plus.
Yep.